Okay, so next we begin to look at two very important functions in the study of algebra. The first is a homomorphism. Let the set S together with the binary operation star and the set S prime together with the binary operation star prime be two magmas a homomorphism is a function which we'll call phi, mapping S into S prime, such that for every pair of elements, A and B, in the set S, phi of A star B is equal to phi of A star prime phi of B, where the elements phi of A and phi of B are elements in the set S prime. So notice that in the equation, the operation on the left comes from the structure consisting of the set S together with the binary operation star, and the operation on the right comes from the structure consisting of the set S prime and the operation star prime. The homomorphism is said to preserve the operation. Essentially, a homomorphism states that performing the operation star on the elements in the set S is fundamentally the same as performing the operation star prime on the elements in the set S prime. Okay. An isomorphism is a bijective homomorphism. So given a homomorphism, if that function phi is also a bijection, then we call that function an isomorphism. Definition: a structural property is one which is preserved by isomorphisms. Now, two obvious structural properties, well, I say they're obvious, include the cardinality of the underlying set and the type of structure. When we demonstrate that an isomorphism exists between two given structures, we say that they are isomorphic, and this is denoted S star is isomorphic to S prime star prime, or more simply, S is isomorphic to S prime if the operations are understood. Now, when we demonstrate that an isomorphism exists between the two structures, then we say those structures are isomorphic. And whatever structural properties one structure has, the other also has. Now, as the function phi, the isomorphism, is a bijection, necessarily the cardinality of the two sets in the structure must be the same. And we will also demonstrate that if two structures are isomorphic to one another, then they must be the same type of structure. So when two structures are isomorphic to one another, we say that they are algebraically equivalent. So what do we mean by algebraically equivalent? Well, first and foremost, we mean that the that the relation isomorphic to is an equivalence relation. So next we'll prove that. Isomorphisms are equivalence relations. Okay, so to prove that a given relation is an equivalence relation, we need to demonstrate that it satisfies three properties: that it is reflexive, symmetric, and transitive. So first, we'll demonstrate that an isomorphism is reflexive. For this proof, let set A together with the binary operation star sub A, set B together with the binary operation star sub B, and set C together with the binary operation star sub C be magmas So first, define a function phi from the set A into itself by the identity function phi of A equals A. Then the identity function is certainly a bijection. And so for every two elements, A1 and A2 in the set A, we have that phi of A1 star sub A, A2, is the element in the argument, that is A1 star sub A, A2. And as the function phi is the identity function, this is the same as phi of A1 star sub A, phi of A2. And so the function is also a homomorphism, and so the function phi is an isomorphism. And hence the structure A is isomorphic to itself. That is, the equivalence relation, or rather the relation isomorphic to, is reflexive. All right, so next we demonstrate symmetry. Suppose that A is isomorphic to B. Then there exists a bijection phi from the set A into the set B, such that for every pair of elements A1 and A2 in the set A, phi of A sub 1 star sub A sub 2 is the same as phi of A sub 1 star sub B, phi of A sub 2. As phi is a bijection, it is a one-to-one correspondence, and so the set B is precisely the set of all images of the elements in the set A. Further, as phi is a bijection, there exists the inverse function phi inverse, which is a map from the set B into the set A, which is also a bijection. And so for every two elements, phi of a sub 1, phi of a sub 2 in the set B, we have that phi inverse, and I'm going to use this equation, but I'm going to use the right-hand side first. So phi inverse of the pair, or of the product, phi of a sub 1 star sub b of phi of a sub 2 is equal to phi inverse of phi of a sub 1 star sub a sub 2. The inverse image of a direct image under a bijection is this a sub 1 star sub a sub 2, where the element a sub 1 is the inverse image of the direct image of a sub 1, and the element a sub 2 is the inverse image of the direct image of a sub 2. And so the function phi inverse is both a bijection and a homomorphism. And so phi inverse is an isomorphism. And hence, the structure B is isomorphic to A. That is, A isomorphic to B implies that B is isomorphic to A, and thus the relation isomorphic to is symmetric. Okay, so next we demonstrate that the relation is transitive. Suppose that A is isomorphic to B and B is isomorphic to C. Then there exist bijections F from A into B and G from B into C, such that for every pair of elements A1 and A2 in the set A, F of A sub 1 star sub A sub 2 is the same as F of A sub 1 star sub B, F of A sub 2, and for every pair of elements B sub 1 and B sub 2 in the set B, G of B sub 1 star sub B, B sub 2 is the same as G of B sub 1 star sub C, G of B sub 2. Now, as the functions f and g are both bijections, the composition G of f, which is a map from the set A into the set C, is also a bijection. Now, as the function f is a bijection, the set B is precisely the set containing the images under the map F of the element A. And so for every pair of elements A sub 1 and A sub 2 in the set A, we have that G of F of A sub 1 star sub A sub 2 is the same as G of f of a sub 1 star sub b f of a sub 2 and this gives us G of f of a sub 1 star sub c G of f of a sub 2. And so the composition is both a bijection and a homomorphism. And so the composition is an isomorphism. And hence, the structure A is isomorphic to the structure C. That is, if A is isomorphic to B and B is isomorphic to C, then A is isomorphic to C, and thus the relation isomorphic to is transitive. And so as the relation isomorphic to is reflexive, symmetric, and transitive, it is an equivalence relation. Okay, so before we look at structures that are isomorphic, we're going to look at structures that are not isomorphic. So, first example, the set of integers together with addition is a magma, but the structure is not isomorphic to the structure we looked at in the first example with the complex numbers and the operation star, where the operation star is the multiple of a complex number and the conjugate of the second. So first, I need to demonstrate that the integers with addition is a magma. So notice that for every pair of integers, their sum is always an integer. And so the set of integers is closed under addition, and hence set of integers together with addition is a magma. Now, notice that the underlying set in this structure is the set of integers, which is a countable set, and the set of complex numbers is uncountable. And so, as the cardinality of the set of integers is that transfinite number aleph null, and the cardinality of the set of complex numbers is not aleph null, it is not countable, it is uncountable. No bijection exists between the set of integers and the set of complex numbers, so no isomorphism exists. In addition, the structure consisting of the set of integers with addition is a different type of structure than the set of complex numbers under the operation star. Recall that this structure, the set of complex numbers under the operation star, is a magma but is not a semigroup, whereas for every 3 elements A, B, and C in the set of integers, it does not matter how we group the terms. When we perform the sum, we always obtain the same result. And so the structure consisting of the set of the set of integers together with addition is a semigroup. And so it is a different type of structure than the complex numbers under the operation star.